Welcome everyone. Today I have the pleasure to introduce to you Giorgos Papageorgiou. I probably butchered this name, though, sorry. He has a background in theoretical physics with a PhD in mathematical physics from Heriot-Watt University. He has worked on rock physics modeling of partially saturated carbon dioxide rocks with a short stint in Trondheim at NTNU, where he worked on seismic modeling of anisotropic partially saturated thin layers and their effects in seismic wave propagation before returning to the University of Edinburgh to work on seismic rock physics as a research associate where he's currently based. So Giorgos, why don't you go ahead and you can share your slides, and yeah, welcome and thank you for giving this presentation.
Yeah, thank you very much for inviting me. And Seb, I will nominate you when I ask a question to say yes or no. Can you see this?
Yes, I can see this.
On that note, let me tell you about the attenuation and seismic modeling of injection fluids. Okay, I will start by showing you something with very little context. This is five experimental measurement kind of graphs. They all concern rocks that have been measured in some sort of triaxial set, and they've all been measured in different labs, different frequencies, different rocks, and I think different fluids. Some are air, water, and some are CO2 water, and they all have some sort of acoustic property on the y-axis, and water saturation on the x-axis, and they are all very different. Some very anisotropic, some totally isotropic, and they share one common characteristic, which is going to be quite central in my talk. And this common characteristic is that these rocks, these two are shales. This is a limestone. This is a synthetic sandstone. This is a real sandstone, I think. So all these rocks have been desaturated from water, and they have had a fluid that is either air or CO2 that is softer than water. And they exhibit this bizarre behavior where their moduli, or their velocities, or whatever you want to call them, increase. So you have things that are 100% water saturated, a porous medium with a stiff fluid, and then you add a soft fluid, and all of a sudden you see this bumpy increase in their moduli. It's common to all of them, and that is counterintuitive. Some might say unphysical. It's not unphysical. I will show, but it's counterintuitive, and it's not an issue with error. I know these don't have error bars. Rock physicists are notorious for not putting error bars, but they all exhibit this injection, or, like, if you will, replacement of a very stiff fluid with a softer fluid, yet their moduli increase. Okay, so I just want everyone to start thinking about why this may be the case, and hopefully I will provide at least one plausible explanation by the end of this talk. So let me now motivate essentially what I'm going to say. I want to show work that is based on theory, but has some experimental verifications, and it is essentially a framework in rock physics, which is a way to think of dispersion when you partially saturate porous media. It's very important for CO2 monitoring. And I will show that it has also implications in what is now a trendy topic, hydrogen storage in porous media. I will take you through some theoretical work that we've done in Edinburgh, some experimental results that validate this work, mostly obtained in the National Sonography Centre in Southampton. And I will show some impacts that this might have, mostly in field data, and how these results impact seismic signatures, and how, in particular, you can see potential impacts of relative permeability in seismic signatures of partially saturated rocks. When I say seismic signatures, I mean mostly exploration seismology, so I noticed Tom Hudson is in the audience, and these guys do tomography, and they go very deep, and they look at earthquake sources, and I'm talking about much shallower things mostly, but potentially a collaboration is underway, and we can see these things in these tomographic Q measurements that these guys get. And finally, I will motivate how these things can be used so they will understand seismic data in light of these features. So I will do this in 4 parts, more or less. I will first describe what the subtleties are in fluid effects. Then I will show you how we treat the subtleties using a sort of effective medium modeling theory in Edinburgh. Then I will show the impacts on these in seismic data and motivate future work, actually. So there's 3 things that make fluid effects, partially saturated rocks, subtle. I have 3 images here. The leftmost is from Dvorkin and Noor from 1998. The middle is from Batzel et al. 2006, and the rightmost is from a former student who was co-supervised by Mark Chapman in Edinburgh and Angus Best in Southampton. And the leftmost shows you that the P-wave velocity depends not only on water saturation when you try to measure the behavior of a porous medium under partial saturation, but also on the path on whether the way that you saturate this porous medium is an imbibition way or a drainage way, and this is very impactful on essentially whether you can invert this or not. That means in particular that this hysteretic behavior, this labels are patchy and homogeneous, you could replace these with imbibition and drainage. So you can see that there is a hysteretic behavior, and that means that you can't really say from a velocity measurement what sort of saturation you have. And that is ambiguous for trying to invert for many things. How much CO2 you have, how much gas you have, whether it's worth drilling or not, and things like that. The second subtlety comes from the way this partial saturation affects the attenuation and dispersion. So I'm showing here now the horizontal axis is frequency, and I'm showing what is called the standard linear solid model, which is this sigmoid curve on the top. And this shows you how velocity disperses, how it has different values for different frequencies. And it is conjectured that this is a very good model because it's A, causal, and B, it has some nice properties anyway. And it's conjectured that this characteristic frequency, the bit that this thing kicks off, is dependent on the mobility of the fluid seas, essentially, in the rock. If you have a low mobility, you have some frequency. If you have high mobility, different frequency. And the question arises, what happens when you have partial saturation, because the mobility changes under partial saturation. This was a conjecture. This was drawn by hand, essentially, from Batzel. But there is the idea that if you have a different mobility, then the way you saturate a medium, if it's imbibition or drainage, should have different values of mobility for the same saturation. So the ambiguity carries in this dispersive medium as well. And finally, there is the ambiguity associated with what happens when you have an anisotropic rock, right? And it can be argued that there's no rock that isn't anisotropic. So some work that Kelvin Amalakwu did, who's now in Exxon, showed that there is this fluid distribution that affects also how anisotropy is manifesting itself when you try to measure it. And Kelvin did this experiment that he actually took rocks and he put them in a hydration chamber, and he started saturating them and then started imbibing them, and he showed that there is this very complicated sharing property where you might have fractures having a very, very pronounced effect or a very minimal effect depending on the way you saturate these rocks. So we have 3 things here. we have we have three reasons why subtleties in rocks manifest themselves through fluid partial saturation. One is the way that the fluid distributes in the rock, and this is the patchy and uniform scenario that I showed before. One is the way that it affects dispersion, and one the way that it affects anisotropy. So I'm going to tackle these three, okay? The way I tackle these is based on a very well-established but mathematically, I don't want to say complex, but mathematically involved theory, and that comes from Eshelby in the 50s. Eshelby was a very smart man who showed what effective medium, what an elastic matrix with an embedded ellipsoidal inclusion behaves like elastically. And then people took that and started discussing how we can approximate the rock by having an isotropic background matrix, and then start adding these pores, and they realized that pores can be largely split into these bimodal, let's say, distributions, and they are centered around a compliant and a non-compliant bit. And the compliant looks more or less like sphere, and the non-compliant bit looks like a flat ellipsoid. And then people started describing how fluid behaves, because if a fluid is inside a compliant pore, then it gets squeezed when you have a pressure wave passing through it, whereas if it's in a spherical pore, it doesn't get squeezed. And then Mark Chapman in 2003 had a paper out that he showed that fluid does squirt when a pressure wave passes through a matrix that contains these types of pores, and that has the effect that fluid moves between the compliant and the non-compliant pores, depending on whether you're in a pressurization or a depressurization part of the cycle. And that's the physics behind it. The maths behind it is relatively simple. You describe essentially the effective elastic constant of your overall medium with the elastic constant of your background matrix, and this is the Cij0 here that I have. And then you have some sort of activation function, and this activation function essentially is what I call here a standard linear solid, and this is the thing that determines how the fluid that moves in and out of compliant, non-compliant pores, essentially because of its viscosity, appears, makes the whole thing appear a little stiffer, and that has a certain tau value, a certain characteristic frequency that it takes over, and that is determined by how far away these guys are. And then you might do that by adding a set of compliant and non-compliant pores in one scale, and then you might say, right, actually these rocks are anisotropic, so I might as well start adding what I call fractures, but I might as well model fractures by these larger ellipsoidal compliant pores. And every time you do that, you would add another activation function, and that would be dependent on how big these guys are. And you have a way like that to describe how a fluid saturated porous medium behaves when the dispersion is triggered by this fluid movement. This is called the squirt flow model. And this thing looks very simple. Is what I call the standard linear solid earlier, and this is the shape of this activation function. This is where the say correction elastic constant comes into play, and this depends on two things. Each one of those little activation functions depends on two things. You need two things to describe it, let's say. One is by how much does it disperse. It has a low frequency limit and a high frequency limit, but it just it has a transition frequency as well, and this is the other thing it depends on. So you need two things to describe it. One is where this transition happens, and the other is how far apart is the high frequency limit, let's say, and the low frequency limit. And I've plotted this here against frequency, and I have this this omega tau, scaled it to 1 so that this thing happens at this particular, say, tau. you have one of those tau, one of those different transitions for every set of inclusion you include, okay, you add to this effective medium. And what does it look when you sit down and do it? So if you think about a matrix that you have that is populated with randomly oriented these ellipsoidals, these microcracks, and then these microcracks would not have a preferential direction in which they disperse your matrix. And here I've done that. I've said, right, I have a Cij that is a solid matrix, and I've added quite a lot of spherical pores and randomly oriented ellipsoids. And I've taken this mathematical model and I've shown how it behaves, and I've tuned that to disperse at the frequency where essentially you have the scale length of say that is similar to the grain size. And I'm showing here 3 elastic constants, and all 3 are on top of each other. I'm showing the compressional modulus against the 1,1, the 2,2, and the 3,3 direction. And because these microcracks are very close together to the pores, then this thing disperses at a high frequency. I have here an seismic observation frequency for exploration seismic. And where these things essentially start dispersing, which is in the ultrasonics, and they all C11, C22, and C33 disperse together because there's no preferred direction. Then if I start adding fractures to this, if I put the fractures in the C11, C33 direction, you will notice that C11 and C33 disperse very little, because the pressure wave that propagates along that direction has very little effect on the fluid, because we are looking at the fractures from the side, let's say. But obviously C22 now looks at the fractures as a normal, and because these guys are larger than these microcracks that I had here, this transition frequency from where it was here at the scale of the pore now is larger. Now the fractures are larger, so this transition frequency has lowered a bit. And then you can do that as many times as you want. I've added another fracture set here, and this is now on the plane of C11, C22. So C11 and C22 do not disperse very much when they encounter these large fractures, but because C33 is normal to these fractures, a wave that passes from up down induces this fluid flow, and you have this large dispersion that occurs. And now these are larger, so they occur in a lower frequency, and essentially that's how you create as many fracture sets as you want, and it's very mathematically tractable to do this. So I could just go on. So this is what happens essentially simplistically from the point of view of mathematics, and this happens when you have a fully saturated matrix with these fully saturated fractures that communicate fluids between each other. And then my work was to try and see what happens to this whole system when you partially saturated. What happens when you have 2 fluids that are miscible in the pore space? I tried several different things. We discussed about how the effects of capillary pressure be taken into account. We thought about one thing, the other, and we ended up saying, well, the way to describe these things, you always have a drained and an undrained experiment, thought experiment, and in one case you have this thought experiment where everything is sleeved, so you don't see an actual separation of fluids in the pore space. You see an effective fluid, and then when you do the unsleeved part of the experiment in your head, then you see that the 2 fluids affect your matrix. And then we thought, well, in this situation it's very simple to describe this effective fluid, and that's what we did, and this is how we ended up with this theory. So we considered that the fluid mixture is an effective fluid, and then we said, if each of the individual fluids in the pore space have a different response to the stress, then this response to the stress should be weighted by a constant, And that would mean that this constant is a way to incorporate capillary effects. Say that the wetting fluid pressure responds to the stress a little less than the non-wetting fluid pressure. By how much? Well, let's call this how much a constant. And we introduced this constant, and we took the bounds, and it has very strict physical bounds. If this constant is 1, we call this small q. If this constant is 1, then both fluids respond to stress in the same way, and if the constant is less than 1, then the stiffer fluid takes a larger load. And we just did the same kind of math on the fluid exchange for the compliant and the non-compliant pores, and we found two major things. The last bullet point here was the bit that people care about mostly in the oil industry, and that is because we derived this Brie empirical formula, which is very widely used in the oil industry, but we derived it from first principles theoretically, and it's not quite the same formula, but it's very similar, and it has this shape. If you know what a Brie empirical formula is, then this is a physics-based Brie empirical formula, if you will. But also the other thing that we understood was that we have a way for this to prescribe how the standard linear solid characteristic frequency varies when you're in the partially saturated regime, and that is by finding a way essentially to add the mobilities together. And then this is bizarre because we have a way to add these mobilities, and the effective fluid sees this effective mobility, which is the thing that determines where this transition happens that I showed before. So this little q affects the transition between the mobility when the porous medium is saturated entirely by water and the porous medium is saturated entirely by CO2. And what is bizarre here is that these permeabilities here, so this is permeability, this is viscosity. These permeabilities are effective permeabilities, which mean that the overall mobility of this thing, the overall frequency that is, right, is lowered much more than the individual mobility. So if you have a porous medium and you try to pass two fluids through it, then you see that the permeability of this thing is much lower than the overall permeability. The two mobilities don't add to one, let's say, the two effective permeabilities. And that has some consequences, so I will try and describe them a little schematically. Consider having a brine saturated porous medium that would have a characteristic frequency where it disperses. This is for an isotropic case. And consider taking this and then saturating it entirely with CO2, and then it will have a different characteristic frequency. Would be higher because the mobilities are different, and the ratio, if we scale the brine saturated porous media characteristic frequency to 1, the characteristic frequency of the CO2 saturated porous medium when it's fully saturated would be larger by the amount of the ratio of their viscosities. And I have shown this here, and I've shown this here as well. But now we have this constant Q, which essentially represents, as I said, the well, we believe it represents a form of capillary pressure, and this constant can absorb the effect of the individual fluid pressures response to stress, let's say. And you have two ways of prescribing this. One is the patchy saturated version, where the wetting fluid takes on more of the stretch, more of the stress, and the uniform saturated case, where they both take on the same stress. And you will notice that in one of the two occasions, you have, if you are in the low frequency regime, let's say, so here I'm in the low frequency regime, nothing disperses. You have this gradual decrease. Every one of those red curves is 10% saturation. This is versus frequency, right? So you have this gradual decrease, and this is the patchy saturated kind of like gradual decrease that you have that you may have or seen in the literature. And if you're in the uniform saturated case, when this parameter Q is equal to 1, then you have the other thing that you may have seen already, and that is the moment you add some soft fluid, then the modulus drops, and then you have very little variation, so you can't distinguish. So this is 100% water saturation, this is 90% water saturation. So 90% water saturation to 0% water saturation differs very little. And these are situations that this module captures. But the interesting thing is that if you consider making a measurement around here, say, because you have this lowering of mobility, then this characteristic frequency of the whole thing moves to the left. So you have a wider band than this here. So from this step, if you are making a measurement around here, then you have an increase before you start decreasing. So you have this little bump, and you don't see that when you have a uniform saturated rock. If you're making a measurement the same frequency, a uniform saturated rock would drop a little more gradually, and then drop all the way to what you would expect. And the situation, the high frequency regime, which is where none of this happens around here, is as you would expect again. But there's this weird phenomenon that happens when you are essentially having this experiment or observation done in a range where you expect to see dispersion. And this is a different way of showing this. I have a water saturation here and have an effective permeability, and this is how the relative permeability of a rock is prescribed, and this is according to a model called the Brooks score model, which is very standard. And what I've shown here is how this effective permeability affects the characteristic frequency when you go from fully water saturated to CO2 saturated porous media here. And you have two ways of going from the characteristic frequency of water all the way to the characteristic frequency of CO2. One is a uniform saturated pathway, let's say, excuse me, and that lowers your frequency a little bit, and then goes to the other endpoint, which is the way that this model should behave. And you have a patchy saturated pathway, and that has a larger, a larger lowering of the frequency, if you will. And the conjecture that we have made is that this lowering of the characteristic frequency overtakes by dispersion overtakes the effect of the lowering of the modulus. So the dispersion is larger than the lowering of the modulus due to the addition of a soft fluid, and that is why we think this little bump appears in people's experimental data. So let me go to these experimental data. So this is exactly what I said, that there's a bizarre prediction here, and this is that you might have a dependence of the elastic constants from the relative permeability, and that under certain circumstances can lead to dispersion being larger than the softening due to fluid replacement. Okay, and of course you have this dependence both of the elastic constants and the attenuation, and as a consequence, because you can create this model with different types of inclusions of anisotropy from the fluid content. So, where have we observed it on our own lab? I will show very briefly a couple of, because I'm not the right person to ask about experimental results. So if you start asking me about this rig and what transducer they used and blah blah blah, I don't quite know how to tell you these things. But this is one in a set of many experiments that were done in Southampton, the National Oceanography Center. I can tell you that the fluid pressure here is around 20 MPa and the temperature is around 30 degrees. And this is CO2 and water, and there is an imbibition and a drainage curve, and we tried to see what goes on, and we did show that the rock behaves differently under imbibition and drainage, and also we saw this kind of increase in modulus for one of the two, for the patchy saturated case, let's say. And this is a fractured, an artificially fractured rock, and we roughly observed the amount of dispersion that we would expect on the P waves, and very little on the shear waves, which is according to what you would expect again. There's very high difference in the shear waves here, and there's more complicated effects because the dry measurements were a bit higher, blah blah. But we actually managed to observe more or less what I talked about. And this was published in GRL, I think, in 2020. And these are the other things that I showed where people have published, and they have shown that the moment you add the softer fluid, you might have an increase in modulus briefly. This tends to happen in the high saturations because then either the density effect or the modulus effect overtakes everything, but they are observable. These, for instance, I have modeled the data from David Sevchik from 2008, where he did the experiment with Mancos and Pierre shales, and one of the two experiments did actually consistently show this little bump. Then there's this Valais paper where it's shales, I think, again, and this data set as well. I have had contact with people who were participating in these measurements, and they are not an artifact of errors. They are actually measurements that show that there is an increase of the modulus. So hopefully I have offered a little bit of an explanation of why this happens in the lab. Now I'm going to tell you what happens if you disregard this, and you might be seeing it in your seismic data. The main thing that might change is the quantitative interpretation of how much fluid you have. In particular, when you're talking about CO2, CO2 is very particular here because it has a viscosity contrast. It has a very golden sweet spot, let's say, and how it changes properties with respect to water. It has a viscosity that varies very much because it's the critical point is within reservoir conditions, and it has a modulus that varies very much. So you're very likely to see these effects with CO2. So that's why I'm talking about CO2. But this is applicable to most water, or to most immiscible fluids saturating a matrix. So the things that this might have impact to in seismic is frequency AVO. You might see this frequency effect in a different AVO signature under different frequencies, and that might be an indicator for fluid. But also thin layer tuning and how attenuation in thin layers occurs. People don't normally talk about attenuation in exploration seismic because they assume it to be very low, but there is the conjecture that thin layers attenuate very much, and the rest of a reservoir doesn't. And if that is the case, then there is an issue that I will describe with quantifying how much fluid you have. And finally, there might be a way there, because permeability affects the attenuation, there might be a way to use elastic measurements to derive some form of transport properties of a reservoir, which would be very cool, in my opinion. So I'm going to make a little deviation because this is concerning hydrogen, and there is a little application of hydrogen which I've just got a project on, and I would like to talk about that. And that is that we used all this modeling for a very novel kind of application, and that was to see how visible hydrogen would be. There is an idea that we could use porous medium. We could use the subsurface as a kind of storer for hydrogen that is produced during the windy months, let's say, or the sunny months, and use it when there's no wind or there's no sun. So we use it as an under subsurface battery, let's say. So we did this commercial project in which we explored the possibility. There was an anticline 5. We explored we kind of did some forward modeling to see whether this anticline would be a good place to store hydrogen. And this was mostly a desk study, but essentially what we did is we took some very old wells and we said, right, let's look at this target here, and that's the target here. Let's assume the rest is overburdened. Let's saturate it with hydrogen, and let's see when we start seeing it. And then we came across this problem, and that problem is that in order to store hydrogen somewhere, you need to have a pressurizer below the hydrogen so that you can retrieve it later. And this pressurizer has to be a very, very light gas. And the light gases, if you have, say, a reservoir and you have this sequence where you have a caprock, a hydrogen, some sort of cushion gas that pushes it so that you retrieve it later, then this interface, this red interface, is seismically invisible. And we looked at, we did this commercial project and we were like, oh wow, that we won't be able to see hydrogen even if we were to put it there. And then we decided to think of under which circumstances would we actually be able to see it if the dispersive properties of the two gases, even though they're elastically similar, maybe their dispersive properties are different enough to induce a sort of reflection coefficient that seismically might be visible. And what we did is we said, right, let's assume that the smallest visible reflection coefficient is somewhere here, 0.01 or something as an absolute value. And let's see what this difference in viscosity does to the same porous media if you have a hydrogen, a cushion gas. And this interface is seismically, let's say, is an interface. About the mixing between the two gases is about a meter or two or something, I think, from modeling, from fluid modeling. And then we found that CO2 as a cushion gas actually has quite a wide band. This is frequency again, has quite a wide band where it makes this reflection coefficient visible. So then we wrote a small proposal to discuss and find out whether there's application there to use dispersion to see where the hydrogen is, because it would be invisible otherwise, and it would be very expensive to use hydrogen as the cushion gas. You would lose quite a lot of it if you were to inject the first time. So this is an ongoing project. This is with the National Oceanography Centre in Southampton. The project is called CHORUS. And this is the preliminary results. I have not validated these results. This is the first time I show these, but they're quite interesting in that they show that there is. So we used nitrogen because it's very dangerous, essentially, to compress hydrogen in the lab. And the guy that operates the lab in Southampton is a careless guy, so I wouldn't trust him with compressed hydrogen. He would make a boom noise. So we used nitrogen as a proxy, and we looked at what the attenuation of a rock is, the same rock under carbon dioxide and nitrogen, and we saw that there is a little bit of a difference here under saturation, and then this means that there is a range where this interface would become visible. And that's because there's a contrast in attenuation. And the inspiration for this is a paper that is a very interesting paper, actually, that I recommend. It's a paper that was written by people in Calgary and Cruz, and they did this very quirky experiment. And the quirky experiment involved a tank of water and transducers that they obtained ultrasonic data under common offset, so near offset, no far offsets here at all. And they had a blob of aluminium, and next to it they had a blob of butter, a Crisco, the type of butter. And they started taking ultrasonic measurements and essentially do this little, the equivalent of a seismic survey. They drag their receivers along, and they obtained this profile. And you will see that they got a very decent reflection from the Crisco water interface, which from this schematic looks straightforward. But if you look at the actual acoustic properties of Crisco, you will see that the reflection coefficient between water and Crisco is almost zero. So there's no way a near offset survey would obtain a reflection coefficient at the Crisco water interface unless there is some form of anelasticity, some form of some form of phase, let's say, okay? And then they attributed this striking reflection to the difference in attenuation between water and Crisco. And they did that using a constant Q model, which is not quite, let's say, it's not causal, but they assume that that's the reason. So we did more or less the same thing, assuming a causal interface, and that's what we're expecting to use to see the hydrogen when it's pushed up by CO2. So that's one application. Another application where this viscoelasticity issue is important is thin layer tuning. Here this looks nothing like the rock physics model I showed you, but I assure you it's exactly the same thing. It's just mathematically simplified so that seismologists that deal with exploration understand it, and they don't give me lip about using my own model. I've used this most general standard linear solid model, but I assure you this is the same model as before. So what we did here is we said, right, what happens to the tuning? Tuning is a method that people use to find the thickness of layers that are below seismic resolution. They see little blobby things. I will show you how. They see little blobby things. They say, right, this is X thick and Y thick and so on. So what we did is we said, right, let's assume we have a 3-layer system, a wedge model, which is the standard way of modeling tuning. And let's assume that the middle layer has an acoustic impedance that is viscoelastic, and is viscoelastic according to the standard linear solid model. And let's take the amplitude spectrum, and if we were to have an elastic interface, we would have an amplitude spectrum that is straightforward. It would have a minimum at when this omega delta t is of a certain type. But when we do this with a viscoelastic acoustic impedance in the middle layer, then we have a phase. So this omega delta t is no longer an integer multiple of 2 pi, and you get a maximum, but it now has a phase. And that is significant in estimating layer thickness. And I will show you how. We did this, we modeled the Utsira sandstone there in this context, and that has been done many times. But what we assumed here was that we have this caprock, and we have the CO2 sand wedge and the water sand wedge below, and that's the same sand. And we did that 2 ways. One way was non-dispersive, and the other way was dispersive. And you will see that there is a little maximum here in this. There's a reflection, there's a maximum interference between the top and the base reflection, and below that you can't really see how thick the layer is. It doesn't look like a wedge, it looks like, you know, it's just a wave interference anymore. But that blob here, where it happens at, I don't know, this is arbitrary, but it's a function of how big the wedge is. It changes if you assume that this layer is viscoelastic. So you have one way of modeling it, and this is large here. And you have another way of modeling it, and it changes a little bit. And that means that you don't quite know. This is the way you discriminate about how thick your wedge is, and you don't know whether what you're measuring here is the thickness of the wedge or the thickness of the wedge plus a little bit of viscoelasticity. And that might mean that you're off by a few meters, and a few meters mean a lot. If you're talking about a reservoir and you're looking at for gas, for instance, and you want to drill, a few meters might mean the world. If you are trying to find whether your CO2 is gone and you can't find it, it might mean that it's there but you can't see it, or vice versa, it might be leaking. So it's a very important thing to know whether this thing tunes. So we took this idea and we did the following. I'm going to finish very soon, sorry, and I know I'm probably overrunning. We took this idea and we looked at Utsira, and we looked at a tuning of a bit in Utsira. Utsira is a CO2 storage project. I can't go into the particulars of how and when and blah blah. I hope people have seen this before, but this is a CO2 plume in the Utsira formation, and people have looked at the tuning curves of this particular bit here in this AB curve, and they've taken isofrequency sections, and they've looked at this blob going into 2 blobs. As you increase the frequency, these are under different frequencies, and that means that essentially it has a dome-like structure. It's a bit of a wedge model. And they've measured where does this tune, and they decided that this tunes to the right amount, that this thickness of this thing is something like, I don't know, 8 meters or something. And then they did the same thing using a different method where they have the gas-water contact, and they found by how much this is pushed up, and they got a different value, and this is the black curve here. And they were like, oh, this is an independent measurement, and we've done this spectral measurement, and we find it a little higher. We find it about 2 meters higher. And then I sat down and did the same thing, but I assumed that this little dome here, this little dome here has a Q of 10, and magically this pushes everything down by a couple of meters, and essentially if this is a viscoelastic layer, then it would tune at a different thickness, and it would match the independent measurement more accurately. Of course, this doesn't say much. No one knows how big this thin layer is, but it does actually give an indication of this might being significant potentially. So what are we doing in the future? So we're using all this currently in a couple of ways. Now we have funding, and we are essentially building a software package, and this is a commercialization funding, but obviously we will make this available to researchers. So the idea is we use this well to rock physics, to wave field kind of workflow, and hopefully will spin out of Edinburgh University sometime in the next year, and that is part of what all this is doing. Another part is this hydrogen research. This is what I call the chorus. It's a Exploring the 14, a very small grant in the UK, but we have been in active collaboration with NOC. And in NOC we have some lab work being done. We're taking some more measurements. I'm actually trusting Ismail now with hydrogen, so he's probably going to start doing hydrogen experiments, and we're doing a forward model VSP. And there's a couple of other things that are in the works. We have been discussing recently with people about say how we could use this in a volcanic setting, or I'm talking to this guy who is interested in doing filtering, milk filtering, which is a very bizarre area and irrelevant potentially. But there's many applications anyway, and what I want to say is that if these are of interest, feel free to get in touch. I have an email there for this Mantis project, which is our potential spin out, but my personal email as well is hopefully accessible to everyone. And thank you very much, and I'm sorry to have gone a little fast and have more slides, and that's me, I think. Oh, and before I finish, yes, I want also to say that your students, what a great opportunity for you to submit a paper to this upcoming issue in Geophysical Prospecting, of which I am in the editorial board, I have to say, so as a disclosure. But you have what better way to submit a paper than with a deadline of the 1st of April, and this is very broad. It has the title Rock Physics Contribution to the Energy Transition Challenge. But do think about submitting a paper in Geophysical Prospecting. It's very well read, and the topic is very broad, and there's a fast tracking for students, and finally, all these people are the people that have one way or another contributed to funding this research. And now I can actually shut up and say thank you very much.